from Hall effect, we can measure the drift velocity and determine the sign of the charge carriers. Okay. Next, Hall effect demonstrate the force on moving charge in a conductor placed in magnetic field. So Hall effect demonstrate the force experienced by moving charge, okay, in a conductor placed in magnetic field. Now let us discuss charge carriers. Okay, in conductor contains electrons, okay, as the charge carriers. Clear? And for semiconductor, okay, the charge carriers can be positive, okay, or semiconductor can have positive charge carriers, or it can have negative charge carriers, or it can have both, that is positive charge carriers and negative charge carriers. Today we are going to discuss Hall effect with reference to conductor, and as I said earlier, conductor contains electrons as the charge carriers. Clear? So this is to be noted. Okay. So we consider thin slab, that is conductor carrying current, which is placed in magnetic field. So let us discuss it. Okay. Consider a thin slab. So we take conductor, so we have this. Okay. Now let L be the length of the conductor. Okay. So we have L, length of the conductor or slab, and let W be the width. So W is the width of the slab, and let T be the thickness. Okay. So we have T, which is thickness of the slab. Now if we consider this cross section, okay, then what we find? This is W, okay, this is T. So cross sectional area of the slab is width, that is W, times the thickness. So we have this. So this is to be noted, okay? So we need this. So I'm erasing this. Now let I be the current flowing in this direction, okay? It is flowing in this direction. So current I is entering from this end of the slab or conductor, and let the conductor be placed in magnetic field, okay? B, which is perpendicular and is directed inward. So we have this. So we have this. Now, let us consider this, okay? The axis, okay? Coordinate axis. Let's say this is positive x. And let's say this is positive y. Okay, we have this positive y. And let's say this is positive z. And they are mutually perpendicular to each other. So what we find, magnetic field is acting along positive y direction. Clear? So we have this. Now, let us consider electron, okay? I'm taking single electron. There are many electrons, okay, within this conductor, but I'm taking single electron for study. Now, what we find, the motion of this electron, okay, is opposite to current I. Electron is moving opposite to conventional current. So we need to note this, okay? So I'm writing, let B, this is magnetic field which is perpendicular and directed inward. So we have this, okay? Now, the magnetic field causes moving charge to deflect. That is, moving charge experiences magnetic force. Okay, so we can understand in this way. That is, moving charge experiences magnetic force. Clear? Now, we need to find the direction of magnetic force experienced by this electron. Now we know direction of magnetic force experienced by moving charge, okay? Moving charge is given by Fleming's left hand rule. So this is to be noted, okay? And Fleming left hand rule is directly applied for positive charge, whereas in case of electron, we apply opposite to Fleming left hand rule. So I'm writing to positive charge, and we use opposite to, I'm writing in short, okay, Fleming's left hand rule in this way for negative charge, that is electron, okay. So we apply Fleming left hand rule opposite for negative charge. So this is to be noted. Now let us understand Fleming left hand rule in brief, okay. So this is my right hand, I'm wearing gloves, okay, and this is my left hand. So I orient thumb, first finger, this is called index finger, it is used for pointing, and the central finger in this way. They are mutually perpendicular to each other. So this is my left hand, okay. So this is thumb, okay, and so we have this, okay. So this is thumb, this is first finger, or it is also called index finger, and this is the central finger, okay. So this is the central finger, okay, we have this, and we can see they are mutually perpendicular to each other, okay, they are mutually perpendicular to each other. So we have this. Now from F, okay, just to remember, okay, it represents field. So first finger gives the direction of field. So in this case, field is magnetic field, clear. And from C of central finger, we have current, that is motion of charge. So this gives the motion of charge, okay. So it gives the direction of charge. It gives the direction because current represent flow of charge or motion of charge. So it gives the direction. So it gives the direction, or let's say velocity. Of charge. Direction or the direction of velocity of the charge. Clear? And from T, we have thrust, and thrust is force. So thumb gives the direction of magnetic force, okay. So we have this, because we know magnetic force experienced by, let's say, positive charge, okay. If you have a positive charge, so we have this velocity cross magnetic field. So we have this. So this is magnetic force experienced by positive charge, and the direction of magnetic force is given by Fleming's left hand rule. And as I said earlier, we apply opposite to Fleming's left hand rule for negative charge. Now, if you see graphically, okay, this, we have positive x along this direction. So we have negative x, and electron is moving along this direction. Okay, so this is the motion of electron. So we have this, okay, because we know magnetic force equals q velocity cross magnetic field. So electron is moving along this direction. We have positive z, okay, we can see we have positive z, and we have magnetic field acting along plus y direction. So we have this. Now what we find, we cannot directly use Fleming left hand rule. We cannot directly use Fleming left hand rule for negative charge. So what we do, we see the real direction for electron is along negative x. So this is my left hand, and my first finger gives the direction of field, okay, so it is acting along positive y, and the real flow of electron is towards negative x, okay, and thumb is pointing down. Now I must take opposite to Fleming left hand rule. Opposite to Fleming left hand rule means this, okay, because electron is having real motion towards negative x. I am taking motion of electron opposite, okay, so it is, so we can see this thumb is acting towards positive x. So now I'm taking motion opposite to the real motion of electron, and I'm taking field, or the direction of field is same, so magnetic field is acting along positive y, and I'm taking motion of electron opposite to its real motion. So this finger is pointing along positive x, and thumb is pointing along positive z. So we find electron is experiencing magnetic force, okay, it is experiencing magnetic force in upward direction, that is along positive z. So this electron is experiencing magnetic force which is acting in positive z direction, that is upward. So this is how we apply Fleming left hand rule for negative charge, that is electron. So what we find, electron is deflected upward. So we find electrons or electron, okay, are deflected upward. So I'm redrawing this figure, okay, over here. So electron are deflected upward, due to which the upper side due to which the upper side, okay, of the slab becomes negative and the lower side of the slab becomes positive. So we find this, okay. So we have magnetic field acting perpendicular and is directed inward, okay. So we have this. So we have this. Now, what we find, so I'm drawing in this figure also, okay. Negative charge or charges moves towards upper side and positive charge or charges are present on the lower side. So we find potential difference between the upper and lower face. So we can measure potential difference, okay, between these two face. Clear? And this potential difference is called Hall voltage. So what we are getting is that we are getting electric field which is directed from the lower side to upper side of the slab. So we are getting electric field. Clear? So we are getting electric field. And we can see electric field which is produced is perpendicular to magnetic field. So we are getting transverse electric field because it is perpendicular to magnetic field. So this is to be noted, okay. So I'm writing so I have written electrons are deflected upward due to this electric field, okay. So we have negative charge on the upper side and positive charge on the lower side. Electric field is set up across the slab. So we find this, okay. So we have potential difference between these two face, that is potential difference between the upper and the lower face. So the PD, potential difference, or this is also called Hall voltage across the conductor, okay, is measured, and then Hall electric field, okay, Hall electric field, or simply we can write Hall field across the slab or conductor, across the slab or conductor is calculated, and we know electric field E equals potential difference by, let's say, distance, okay, or we can simply write in this way, V by L. So this is in magnitude, okay, or we can write in this way also, equals dV by dL in magnitude. So we can write Hall field and we get uniform field. Okay, so I'm writing over here. So this equals Hall voltage. So let us denote it by symbol VH by distance between these two face, and this is W, that is width, by width of the slab, and it is W. So Hall field is electric field. Okay, so we can write in this way: EH equals VH by W. So we have this. So let us call it equation 1. So we have this. Now we can see from this figure, okay, or if we look into this figure, electron is having motion along this direction because current is flowing along this direction. So it is the same figure. Okay, so we have this. Now what we find is that electric field is acting along this direction. Okay, electric field is acting along this direction. So we find this. So I'm erasing this. Okay, now we are going to find so I'm erasing this also. Okay, let me call this as figure 1. This is figure 2. Okay, now to find Hall field. Okay, now how we find Hall field? So let's look into this figure once again. This figure. So I'm redrawing this figure over here. So we have magnetic field perpendicular inward. Okay, so we have this, and we have electron. Okay, we have this. We have electron which is experiencing magnetic force upward. Now, as I said earlier, electric field is directed upward. Now, in the presence of electric field, okay, the free electron or the electron experience force. Since there are many electrons, okay, they are moving along this direction. There are other electrons also moving along this direction. So I'm taking only single electron. Okay, now I want to generalize okay, the concept. So electric field is acting in upward direction. Now what we know, electric field equals in general, okay, force per unit charge. So we can write in this way, force per unit test charge. Clear? So we have studied this in electrostatics. So this is what electric force. This is electric force experienced by positive test charge. Now for electron, we can write this relation in this way. Clear? So we can write electric force experienced by electron, okay, from this relation equals minus small e, that is charge on single electron, times the electric field. So we have this. Now what we find, electron experience electric force, okay, and the direction of electric force is opposite to electric field. So we find that. So the electrons or electron, okay, will experience electric force in downward direction. So we find magnetic force and electric force, they are opposite to each other. Clear? So let me represent graphically, okay? We have this. Clear? Now we have electric field acting in upward direction, okay, and we have magnetic force. We have magnetic force, okay, acting along upward direction, that is acting along positive z, and we have electric force which is opposite to electric field, okay, since electric field is acting in upward direction. So electric force experienced by negative charge is towards negative z. It is towards negative z axis, that is opposite to electric field, which is acting along positive z direction. So this is to be noted, okay. Now what we do, now in order to find Hall field, okay, is determined by setting, okay, we need to get a condition at which electric force is equal to magnetic force in magnitude, and they are acting in opposite direction, okay. So I'm writing Hall field is determined by setting, okay, by setting the magnitude, by setting the magnitude of electric force equal to the magnitude of magnetic force. So we have this, and let me do some rough work, okay. This is magnetic force, this equals Q, velocity cross magnetic field. Now what we find, if we write in magnitude, or if we simplify this, we get this, okay. Clear? We have this. Now, if we look into this figure, okay, or if we consider this, then what we find, electron is moving, let's say with velocity v along this direction. Say we have this, clear? We have this. Now, what we find, magnetic field B is acting along positive y. Then we know angle between velocity and magnetic field is 90, okay? Because we know x, y, and z are mutually perpendicular to each other. So using this equation, we can write for electron, okay? For electron, we can write magnetic force equals E times velocity B sine 90. So this gives me magnetic force equals E V B. So this is the magnetic force in magnitude. So this is to be noted, okay? So we can write that is magnitude of electric force equals magnitude of magnetic force. So we have this, and we know electric force equals this, okay? And magnetic force is given by this expression. So this is E V B. Now we are using the symbol EH, okay? Because we are using Hall field, okay? We have this. And let's say from this equation, okay, E cancels out. So what we are getting? We are getting velocity V equals Hall field by magnetic field. We can use H, okay, in this symbol, okay, because we are getting Hall electric field, or we are getting electric field which is perpendicular to magnetic field, okay, and this electric field is called Hall field. So I'm using this, okay, EH. Now this is equation second, okay, and let us denote this, okay. Let's say electron is moving with drift velocity Vd along this direction. So we can write simply in this way, okay, Vd. So if electron is moving with velocity Vd along this direction, then we use this. This is simply a notation, okay. You don't have to be very sensitive. So this is simply a notation. We can simply write V E by B also. Now what we do? Now or we use this, okay. We have I equals NE VD A. So I have changed velocity from V to VD, okay, because I'm going to use this relation for the calculation, okay. So we have this. Now We can write I equals NE VD. And what is A? A is the cross sectional area of the conductor. So in this case, we have A, that is cross sectional area of the slab or conductor. So A is, this A is W times T. So we have this. Now we have this, okay. VD equals I by NE WT. This is equation number 4. Now, from 2 and 4, we can write EH by B equals I by NE WT. So we have this. Clear? Now, from equation 1, okay, we have this. From 1, so I'm writing EH equals VH by, okay, this is VH by W. So we have this. So we can write EH equals hall voltage by W, okay, that is width, and we have magnetic field at the denominator. So we can write in this way. Now this W and W cancels out. So what we get, hall voltage, okay, this equals magnetic field times current divided by N E T. So this is the expression for hall voltage.